Hello everyone, welcome to the next video. So I'd like to remind everyone that the best way to learn from these problems is to try them yourself, give them an honest try, and then watch these answers and solutions. But here we go. So two blocks are released from the top of a building. One falls straight down and the other one slides down a magical frictionless ramp all the way to the bottom. And the question is, which one has these moving faster when it reaches the bottom? And the answer is they're both moving at the same speed. And the reason you can figure this out is that they both start with the same amount of potential energy, mgh. And then when they reach the bottom, it turns into kinetic energy, 1/2 mv squared. Since neither object changed its mass, the masses kind of cancel out. And you're going to solve that both have the same speed. Basically, if you solve for the speed, you get 2gh is equal to speed, and both started at the same height, and both had the same gravitational acceleration, so therefore they both had the same speed. Now, if friction was not ignored, then it would be the one that fell with the faster speed. But because there's no friction on this ramp, they ended up with the same speed. Next one, a hook loss spring is compressed 12 centimeters from its equilibrium, and the potential energy stored is 72 joules. What compression would result in 100 joules being stored? Well, for that, you need to know the spring constant. Okay, so basically, we're trying to solve this. 100 joules is equal to 1/2 kx squared. That's the potential energy for a spring. We want to solve for the x squared, but we don't know the k. And so we're going to use the information they gave us for the first compression, the 12 centimeters and the 72 joules, to solve for k initially. So setting up the equation again, potential energy of a spring is equal to 1/2 kx squared. 72 joules is the first one. 1/2 k is what we're solving for, and they gave us 0.12 meters for the compression. All right, so we have to solve this for k. So what I do is I take 1/2, multiply it by 0.12 squared, and so this basically turns into 72 over 0.0072 is going to be equal to my spring constant, which looks like it's going to cancel out to be a nice even number. 72 divided by that number gives me a spring constant of 10,000. 10,000 newtons over meters? Yeah, 10,000 newtons over meters for the spring constant. So now I can take that 10,000 and plug it in to this equation here. If it fits, close enough. So now I can solve that for x. So multiply both sides by 2 and then divide by the 10,000. Sorry, it's 2 times 100 divided by 10,000. And then finding the square root will give me x. And so square root 2 times 100. Square root 2 times 100 divided by 10,000. Cool. And that gives me 0.1414 meters, or otherwise known as 14.14 centimeters, which 14.1 centimeters is option B. Now, the rate at which work is done is equivalent to which of the following? Increase in potential energy, thermal energy, potential energy, or the correct answer, power. Work over time is equal to power. That's a general rule. Now, when something says the rate at which something is done, that means you take whatever that something is and divide it by time. So the rate at which velocity changes, you would take velocity, or change in velocity, divide it by time, which would give you the rate at which velocity changes, otherwise known as acceleration. So make sure you don't get confused by that word rate. It just basically means to take your quantity and divide it by time. A lot of questions about parachutists. The next question, a parachutist of mass of 50 kilograms jumps out of an airplane at a height of 1,000 meters. The parachute deploys and she lands on the ground with a speed of 55 meters per second. How much energy was lost to air friction during this jump. Well, let's figure this out. So how much energy was lost to air friction during this jump? So how much energy was lost? So basically, they're asking about work again, particularly negative work that was done by the force of air resistance. And so how do we figure this out? Well, she starts 50 kilograms, height of 1,000 meters, and we can figure out how much potential energy she started with. Okay, so we have mgh, and so her mass was 50. Then she had 9.8 for the acceleration, multiplied by the height of 1,000 meters. And so we know that she had 50,000 times 9.8, 4,90000 joules of potential energy to start with. Okay, now parachute is deployed, and on the ground she has 5 meters per second is how fast she's actually moving. Okay, so we can figure out how much energy she had at the end. Now, at the end, she didn't have any potential energy because she was on the ground, but she did have kinetic energy. So how much kinetic energy did she have? Well, 1/2, 50 kilograms, times that 5 meters per second squared, giving me how much kinetic energy she had. She only had 625 joules of kinetic energy. So if she started with 490,000 joules and she ended with 625 joules, that means she lost 49,000 minus 490,000 minus 625, which is barely any different. 490,000 minus 266. Yeah, so that means she lost 489,375,000 joules, which is basically the same thing as option D, 489,000 joules. Lost almost all of her energy using that parachute, which is, I guess, a good thing, considering you don't want your energy when you're about to hit the ground. The last question, the net force acting on a 6 kilogram object is given by this function, 10 minus x times 10 minus x newtons. So Fx is equal to 10 minus x, okay? Where Fx is the newtons and x is the meters. So basically the force is going to change based on where it is. If it's at position 0, so if x equals 0, that means the force is going to be equal to 10 newtons. If x is equal to 10 meters, then the force is going to be equal to 10 minus 10, giving me 0 newtons. How much work is done on an object as it moves from 0 to 10 meters? Well, good thing I just did the calculation for these two values. So the force is going to start with 10, it's going to drop down to 5, which means on average, we're going to have a 5 Newton force, okay? So on average, we're going to have a 5 Newton force to deal with. So how much work is done? Well, work is equal to force times distance. And so on average, we had a 5 Newton force, and we traveled a distance of 10 meters. So that means that we, on average, did 50 newtons of work. 50 joules of work, I'm sorry. Newtons is for force, joules is for work. So option C for that one. All right, guys, I'll see you in the next video.